Hello, this is the Project Ariadne presentation on AI ML based user equipment to access point associations in dense and evolving networks. My name is Edwin Yakub from the Altair Rapid Miner research team, and let's begin. So, in this pictorial, we see a nice visual where we have two users and two access points connected over some D band or higher frequency link. We know they deliver higher data rates, but they are susceptible to line of sight blockages. Now, another user walked into the line of sight between user 1 and access point 1, and the connection is lost. And this needs to be reassigned to another access point. Hence, the user association strategies must minimize these line of sight blockages. And on the other hand, we see that future networks are expected to support massive connectivity for a wide range of applications with diverse requirements. One user may be happy with 10 Gbps, but another might need 100 Gbps. Thus, user association must consider backhaul capabilities, user requirements, and blockage minimizations all at the same time. Hence, the UEAP association is a directional connectivity problem which requires resource allocation, blockage minimization, and it needs to be solved dynamically in dense networks which are evolving, and the solution must adapt. In terms of definition, this is an optimization problem that can be defined by four constraints. C1 shows that one UE belongs or should be assigned to one AP only. C2 states that, of course, an AP can have multiple UEs assigned to it. C3 states that we need to minimize the overuse of access point resources. And C4 states that the line of sight blockages need to be minimized. The same constraints then serve as an evaluation criteria to assess the performance of our optimization and machine learning prediction solutions. Here is a diagram for the hybrid meta heuristic and machine learning framework we developed in this project, which gives us the solution approach. We generate a network model dataset. It is ingested into the online solver. In this case, we used Optaplanner, which provides meta heuristic algorithms. Now they try to solve the network topology, AP resources, UE demands, and produce an outcome. We convert the ground truth found by optimizations into a label attribute and train machine learning models on it. And effectively, we are transferring the path finding or discovery capability of meta heuristics into machine learning model. The data processing and machine learning model training and application is done in RapidMiner. So we have three artifacts. We have a system model, as you can see in the screenshots of the RapidMiner processes. The system model is implemented in RapidMiner processes along with the machine learning and data processing evaluation pipelines. The data sets are generated using the system model. In this diagram, we see that there is a need to minimize or bypass blockages because 5G, 6G, or other higher frequency networks will face blockages. Here we see different colors for dots, which represent UEs in the same cluster that are overlapping each other's line of sight, especially the ones behind or farther away from the AP trying to connect with an AP shown here. So, based on the distance and phase properties, we can find that line of sights can be blocked not just by UEs of each other, but by thick forestation, buildings, and blockades. But another area of interest in LOS blockages is that of partial blockages, because the UEs that are blocking each other are, of course, accompanied by human users who are carrying the UEs or mobile phones. And we have a notion of counting the number of line of sight partial blockers for every UE that is trying to connect with every AP using some inequality conditions that are derived from domain expert knowledge. Hence, we come up with the number of blocking UEs for each UE when trying to connect with any AP, and this step used unsupervised machine learning clustering most of all. We trained that result into a classifier, so into a supervised machine learning model, which performed fairly well with limited data set training that showed the pattern existed. And the green column here is able to uh, predict the same number of blocking UEs in 80% with 80% accuracy. Now we have inducted that model also into our system model because it is efficient to compute blockages using machine learning. But the main target remains that we want to have a supervised machine learning model to predict UE and AP associations. As seen already, we have system model generator data sets, which give us geographic properties of UEs, APs, availability and requirement of resource, and the LOS blockages. We ingest it into a meta-heuristic online meta-heuristic solver, Octaplanner. We write the constraints. It delivers us a solution, which is the assignment as determined by the meta-heuristic algorithm. We come up with a categorical representation of an access point. We train the model to predict it, and then we resolve a particular access point that belongs to that category of the model, to that category of the predicted label. In case there are more than one, we pick randomly one of the access points. This post prediction step is meant to basically come up with an access point assignment quickly, but it may have some loss of accuracy, of course. So we see that we have a dense network in the left diagram where we have lots of blue dots and also quite a lot of access points, which are represented by the red dots. The UEs represented by the blue dots need to be assigned to the red dots. And on the right-hand side, we see the fully connected network. And if we zoom in, we see an access point is connected to several UEs, which provide the best line of sight connectivity with this access point. In a similar way, we can use online optimization concept to generate more data sets which are realistic and also rich in terms of the situations they have seen in the network. We can take a base data set, make some evolution trails by adding UE, moving it, removing an access point, changing the UE resource requirement, or even crashing a UE and removing it in real time. And then we can save the evolved data sets and continue to have more machine learning model improvements because we need more data, we need diverse data, and the solvers give us the ground truth to train the machine learning models further and further. Here is a snapshot which shows the results of an online optimizer. On the left-hand side, we see a fully connected network plot where the UEs are all being assigned have been assigned to the access points. On the right hand panel, we see here that the optimization score, the hard score is 0 as well as the soft score, which means we have satisfied both the resource requirements and the line of sight blockages have been minimized to 0 for a large problem, 10 to the power 1388 in state space size. If we just have a visual inspection of the GBT, which also we trained to replace the optimization results, it looks quite complex. Hence, it proves that there is not an easy mapping, but a complex pattern that it extracted. Here are some of the results from the machine learning model that we just saw. We actually trained 4 models, and we see that even if we train them on 10 or 20%, we are reaching the test set accuracy around 99%. So we do not need to train them on complete data set, and that saves us precious time because in dynamic problems, we need to save on many data sets. Precision and recall is also pretty good in this multi-class problem. Recall is mostly above 96 or 97 and mostly over 99. And precision was almost greater than 99 in most of the cases. Now we can compare the same results predicted by the machine learning model. And here we see that, yes, it resolved to using less number of access points, but some of them now may be overloaded because the machine learning model here is only trained on 2 data sets and only 10% of that data. And it also predicts assignments where the line of sight blockages are minimized to zero for 361 connections only. As we train with more data and more percentage of that data, we see that the number of access points are used more, and also the links with blockers are increased, while those with more blockers are reducing. We can now see the results from an optimized GBT model, which has been trained on 4 data sets using only 10% split. And now we are seeing the improvement is becoming more and more better. 636 connections with zero line of sight blocker. And with a final model, we have 642 UEAP connections with zero line of sight blocker, and the other blocker links are also continuously being minimized. So only 17 links where there are more than 2 blockers. That shows that machine learning has learned the constraints that the meta heuristics solve. And that's a good finding because it is a structural bin packing problem with feasibility and optimality constraints. And that proves that machine learning is useful in these kinds of problems. Training and scoring times of the GBT models show that although training can take a long time in this case, especially when we optimize the model, but on the test set, we are dealing with more than 100,000 data points, and the scoring time is within a few minutes, less than 13 minutes or 14 minutes of time. More important, however, is the ability we gain from the GBT, from the machine learning model, to actually predict only a few number of data points or a single UE need to be predicted to be assigned to an optimal AP. This advantage we did not have with global optimization solutions, and machine learning rendered us this advantage. So, what have we as main outcomes? We have a hybrid solution which provides a demonstration GUI where we have natively integrated rapid minor processes, and we can hence change the problem on the fly. And also, the solution is adaptive. And this also paves the way for us to easily store more training data, which has seen more diverse changes. And this also basically paves the way for frequent or online learning. So thank you very much. This ends the first part of my presentation.